Thanks, Kenno. Good afternoon, everybody. My name is Matthew Farthing, and yeah, this is picking up from where Alex left off in the session before lunch. And it's basically us just sharing this project that we've been working on with a really large team of people from a variety of institutions, with the end goal really of coming up with the best guess for post-release mortality in data poor fisheries. So it goes without saying that there really is global consensus that catch and release is not benign. And there is a growing body of evidence that suggests that the outcomes of a catch and release event and the impact on the species really does depend on the species, its biology, the environment in which the angling is taking place, the various fishing techniques and styles of participation, the individual angler's behavior and their practices, and a suite of other associated factors. And as a result of those intricacies and the fact that recreational fisheries are incredibly variable and target an incredibly diverse array of species, it goes without saying that post-release mortality is incredibly variable. Now, it's that variability in post-release mortality that leads to the psychological phenomenon which I'm calling post-release obscurity, which is the discomfort you feel when someone says, "What happens to the fish when you release it?" And you say, "I don't know." Right? So, and post-release obscurity around the world really hampers effective management. It really does. And that's because even in fisheries where we have a really good handle on harvest and the amount of harvest coming out of recreational fisheries, the fact that we don't know what happens to the fish that we put back means that we cannot estimate total biomass removal, and that really undermines our ability to use catch and release not only as a conservation strategy or in spatial planning, but it also affects our social license and society's acceptance of catch and release as a management tool, but also as a sport, and it also drives a lot of stakeholder conflict. So when looking at previous reviews of the catch and release literature, there really are a couple of seminal papers that Alex alluded to in his talk earlier, but I think one of the key takeaways from that is that these have traditionally been focused on the explanatory variables, which one of the papers calls the determinants of hooking mortality. And while many of them have summarized these mortality patterns across taxonomic groups, different gear types and different methods and different environmental conditions, the truth is that there has been little effort to synthesize these overall post-release mortality across global recreational fisheries, or to develop some predictive power. So obviously, when looking to what management needs, obviously understanding these determinants of hooking mortality has incredible value in shaping best practice, in shaping gear regulations, and in driving pro-environmental outreach. But the truth is that many managers really just also want an explicit estimate of post-release mortality. And while there is a growing evidence body, as Alex said before, there is a rapidly increasing body of post-release mortality estimates. The truth is, there's no way that we're ever going to have this for all of the fisheries around the world. And many managers truly believe that a defensible best guess would suffice. So with that in mind, Kieran Hyder at CFAS shook the money tree and told us that he really wants us to do a meta-analysis of post-release mortality in marine recreational fisheries to support predicting post-release mortality in data poor fisheries. So we started off with the objective of compiling a database of post-release mortality estimates for these fisheries, and then use that database. And then what I will be talking about now is how we use that database to develop this model for predicting post-release mortality, and eventually the tool that we're trying to create to support decision making. So again, if you were at Alex's talk, he would have told you about the large efforts that we went to consolidate this database and to come up with this literature, this database of all the estimates from the literature. So we have 102 eligible post-release publications of post-release mortality with 164 unique estimates for 36 families, 95 species, and from 19 countries. So we are working with a considerable amount of data in the published academic literature. So in using that information, we then move into a meta-analysis, and we chose to adopt a Bayesian approach. A Bayesian approach handled variability really, really well, and also gave an output that also, how would I say, had a really intuitive probability associated with like the range of what it is you could expect. So we undertook a bottom-up approach, and we specified the model with leave-one-out cross-validation in the BRMS package in R. To get this data ready for the modeling exercise, we basically consolidated all of the estimates as proportions. We calculated the standard error of those proportions, and where the standard error was 0, we used the average standard error of non-zero cases. We adjusted mortality proportions of 0 and 1 with a small constant, and then we logic transformed the data. So as Alex also would have alluded to in his talk before, when we started this, we undertook the coding and extraction with a harrowing list of things that we were trying to get from every paper, but we very quickly realized that the reporting was incredibly inconsistent and that we ended up with a pretty limited list of predictors across all these studies, which included individual study ID, the species, the genus, the family, the class, the study method type, the fishing platform, the presence of barotrauma, and whether or not that fish had a swim bladder, which obviously we could determine from the species. Excuse me. Okay. So when specifying this Bayesian logistic regression, after a long process, a bottom-up leave-one-out process, we basically ended up with a model that used study, species, family, the presence of barotrauma, and the presence of a swim bladder. And to talk you through how this model was specified, so we have individual study ID as a random effect, species nested within family as a random effect, and then the fixed effects of barotrauma presence, absence, and swim bladder presence, absence with an interaction term between them. So when looking into the diagnostics of the model that we ended up with, the model's got a Bayes R-squared of about 0.42, which suggests reasonable fit, although there is quite a high error. When looking into the random effects, across the studies, it seems that there is a moderate variation in post-release mortality between families, although there's incredibly high variation in the post-release mortality of different species. There is some considerable variation between individual studies, and when looking into the fixed effects, barotrauma and swim bladder presence certainly played a role. When you look at the conditional effects graph over here, you'll notice that where there is no barotrauma, the outcomes are relatively similar, but for fish with a swim bladder, when you add barotrauma to the equation, there is an increase. Ignore this biologically unrealistic scenario of barotrauma for a fish without a swim bladder. So there definitely does seem to be an interaction between barotrauma and the presence of a swim bladder, which was of course to be expected. So when it comes down to the numbers and our actual best guesses, so the model's fixed effect intercept suggests that the baseline post-release mortality, if you know nothing else about the fishery or the species or anything, is 9%, ranging somewhere between the credible interval of 4.4 to 17%. So based on all of those studies, if you know nothing else about your fishery, that's what you can expect. If you do know that you have a fish that definitely doesn't have a swim bladder, and therefore inherently also wouldn't have experienced barotrauma, that number increases slightly to 9.7% with a similar credible interval. If your fish has a swim bladder, it goes down a tiny bit to 8.2%, but when you add barotrauma, that number goes up to just under 15%, with a much wider credible interval, suggesting some uncertainty. So those are obviously the magic numbers or the best guesses for those scenarios that are really, really data limited. But you can also extract estimates for individual species that are in the model. So for example here, this is an example of some of the extracted predictions data for species for which there is certainly more than at least one mortality estimate in the model. So you can pull species-specific estimates with and without barotrauma. And you can see that, for example, your sea bass is about 6% and then increases to 12% based on barotrauma. And there's a couple of other species there for reference. So you can do the same. You can also pull for family level estimates too, so you can also zoom out to that level if you need to. So moving on from that, now we obviously have this database of predictions, but what we started to do is to try and roll this into an R-Shiny app, which basically is a decision support tool for managers looking to understand the impact of recreational fishing in their fisheries. Excuse me. So the first half of the app is basically a database overview. You can see what work is done in which part of the world, and you can see the papers associated with that information and the information that was used to basically develop the tool. And the second half of the app is focused on actually understanding the mortality estimates for at the different levels that it is that you're looking. So, you could, like I said, you could look at species, you could look at family, if they're in the model's training data. If not, you can zoom out to predictions at a variety of levels. And again, you can download and extract this data should you need to. We're still working on a few bugs in this program and how it presents and how people interact with it, but this will be available imminently. So what are the next steps for this? Well, of course, the first step would be to finalize this decision support tool and to start sharing it and to get people to interact with it. And I think it'd probably be good for us to distribute it to all of you to get some critical feedback first. The next step would be to publish our marine recreational fisheries review, post-release mortality review, and get that moving. We're also looking to kind of work on a catch and release reporting standards paper to try and harmonize the way that we basically report our catch and release data to support the idea of having a global database that's regularly updated, something that you can all access, something that we can all access, and work together to basically get all this information into the same place. Basically, roll regular updates on the database would be really great, and then obviously routinely update and improve the tool. As the research improves, as the amount of estimates improve, and as the taxonomic coverage and regional representation improves, so will the estimates in time. So that's our thinking for now. Also importantly, the idea is to add the freshwater research into this in time, and I know we've been working with Robert and Steve's team on the freshwater side of things, and eventually, in my mind, down the line, we need to figure out a way to incorporate all of the sublethal effects information into the decision support tool as well. Because while you might have an estimate for your fishery for a given species in a given place, there are other things that can increase or decrease those estimates based on the science that we do understand, at least for now. So a big thanks from me to you for all listening. If you want do you want to know anything more about this, please talk to myself or Alex. My picture's missing. Sorry. But you all know Alex by now. So come chat to us if you've got any questions about this. A big thanks to all the institutions and all the partners involved. And of course, a big thanks to Kieran, who basically has pushed this and found a way to make it possible for Alex and I to work on this for the better part of 2 years. So a big thanks to Kieran for that. And any questions? Thanks so much.
Thanks a lot. Very nice. Yes, you were first.
Thank you. Great talk, Matt. Thanks. Just a quick one. Why would the mortality rate increase for a species without a swim bladder? I didn't get that.
Okay.
It went up to sort of 9.7%, and I didn't understand why.
Just give me a second to see if I can get back to it. It's not, I suppose it's not in the absence of a swim bladder doesn't necessarily make you more vulnerable. I appreciate this is something I probably should have spent more time on, but that variable is explaining fish that happen to not have a swim bladder better than the others. So that tends to be your large elasmobranchs and your rays and things like that. So what the model suggests to us, granted there are a lot of bony fish and things that don't, and there would be exceptions to this rule, but it looks like the sharks, for example, like large sharks, and the studies of those might have a higher post-release mortality than the average study of a bony fish, which does have a swim bladder. So it's a little counterintuitive. I understand the way that I probably presented having a swim bladder is worse for you, but I think there are other things that have nothing to do with your swim bladder that make it worse for you. I don't know if that answers your question, Bruce.
Thanks, really great work.
Thanks, Margaret.
And you partially answered my question already about if elasmobranchs are in there.
Yes.
And they seem to be. But are they in general more vulnerable to air exposure, or were you just talking about the large elasmobranchs that generally have a longer fighting time and so on?
So I wouldn't say that, for example, this model can't tell you any of the determinants, right? This model can only tell you overall. So we had to kind of take the broad approach at this stage and say that, like, this estimate represents this fishery and this species, right? So I can't tell you whether air exposure does that from the model. It does look like the post-release mortality estimates of a lot of the big sharks from a lot of that research is relatively high. So I'd be forgetting exactly which ones, but yeah, again, I think that also might be a product of the fact that a lot of those studies have got really long-term data storage tags or the kind of tags that can pick up mortality over a longer period. So that is a potential bias. in the data set. A lot of the bony fish stuff doesn't have that kind of longevity. So I hope that answers your question.
Thanks a lot. Robert had a question, but we take it after.
Okay.
Yeah.
Thanks, everybody.
So we continue.